LLM agent research is moving faster than almost any other field in software engineering, yet the structural approach to building these systems remains fractured. This fragmentation is visible in how different engineering communities report their results. They use 6 distinct labels: self-reflection, prompt optimization, memory evolution, tool creation, harness editing, and self-referential weight updates. In production, this creates a significant bottleneck. A breakthrough in prompt optimization and a new method for tool creation appear to be incomparable, isolated events because they lack a shared technical language. A 2026 survey of the field identified that this fragmentation is an illusion. Beneath these differing terminologies lies an identical, shared mechanical structure. Viewing these improvements as a loose collection of independent tricks prevents engineers from systematically composing or scaling autonomous agent behavior. The survey provides a unifying engineering abstraction. Every instance of an agent improving through experience reduces to a single, universal update operator acting on one of 2 possible targets. This taxonomy organizes the field into a bifurcated system architecture. Every existing technique fits into one of 2 columns, driven by a single continuous loop. The first target, shown in indigo, is the foundation model. This is the parametric core of the agent. The second target, shown in teal, is the operational scaffolding, the prompts, memory structures, and tools that wrap around the core model. Mapping self-improvement onto this strict dichotomy transforms a disorganized collection of research papers into a composable architectural framework. To understand how an agent improves, we must first formalize the modern agentic configuration. We start with the central neural core, the foundation model, formally denoted as theta. Modifying theta requires updating the neural weights. This provides durable improvements, but demands computationally expensive procedures like supervised fine-tuning or reinforcement learning. Surrounding that core is the operational scaffold, or sigma. This acts as the runtime harness for the model. The sigma scaffold consists of 4 modifiable structures: the prompts, the memory buffer, the tools, and the control logic. Sigma functions as the agent's controller. It builds the context window and selects actions without altering the underlying neural weights of theta. This dichotomy exposes a non-parametric layer. Engineers can evolve agent behavior in production by modifying sigma, avoiding the hardware costs of retraining the foundation model. With the structure established, we can define the mechanism of iteration, the self-induced update operator. This loop drives every self-improvement technique in the field. The process follows 4 phases. First, the agent executes a task in its environment to generate raw experience. Second, the system evaluates that experience to extract a quantifiable signal, defined as S sub t. Third, based on that signal, the update operator proposes a specific structural or mathematical change, known as the delta. Finally, the system applies the delta. As the diagram indicates, the change is committed to either the theta core or the sigma scaffold. This sequence remains identical whether the loop is guided by human heuristics or driven entirely by autonomous LLM critics. Architectures like Reflection or Voyager are not distinct algorithms. They are specific implementations of this execute, evaluate, update, apply loop, routed to different targets within the agent's configuration. In the first pathway, foundation model improvement, the update operator targets the parametric core. These updates draw from 3 signal sources: intrinsic generative demonstrations, intrinsic evaluative feedback, and extrinsic exploratory trajectories gathered from the environment. These signals are committed to theta through standard training paradigms, like supervised fine-tuning or reinforcement learning. This pathway creates significant operational friction. Constant retraining demands high capital investment and intensive GPU utilization. However, targeting theta creates durable improvements that persist across all future contexts, effectively upgrading the model's base intelligence. The second pathway, scaffolding improvement, targets the non-parametric elements surrounding the model. Because this avoids the costs of model retraining, it is where the majority of practical, deployed self-improvement occurs today. Within the scaffold, the operator can target the prompts, using population-based evolution or textual gradients to optimize instructions. It can target memory structures, utilizing CRUD operations on vector databases to evolve the agent's long-term recall. It can also target tools and the full scaffold architecture, allowing the agent to generate new API integrations or rewrite its own control logic. Complex systems like Voyager map directly to this framework, functioning as the universal update loop, targeting the autonomous tool creation node within the teal scaffold. By treating the scaffold as an evolvable surface, engineers can scale an agent's environmental mastery without modifying the underlying model weights. While this taxonomy organizes the landscape, it also exposes critical operational frictions, particularly at the evaluation node. There is a recurring gap between mechanism benchmarks, which verify a component updated successfully, and domain benchmarks, which measure if the agent actually improved at its task. If an operator evolves the memory buffer, but memory was not the task bottleneck, the agent's domain performance remains flat despite a successful technical update. Furthermore, using language models to grade the outputs of other language models risks introducing circular logic and systemic bias into the evaluative signal. The boundary of the taxonomy can also shift. Successful non-parametric tools from the scaffold are often internalized into the foundation model weights during subsequent fine-tuning. Without standardized cross-mechanism evaluation metrics, we risk optimizing agent subcomponents that do not translate into system-wide success. This framework is a descriptive map of the landscape, not a guarantee of system safety or convergence. An autonomous update operator can fall victim to reward hacking, causing the agent to diverge from its goals and degrade its real-world utility. To safely control and scale autonomous evolution, we must first categorize its mechanisms. This taxonomy shows that the scattered techniques used today are all instances of one universal update operator, traversing either parameters or scaffolds through a shared loop. For systems engineers, the task is to stop treating prompt management, memory, and weight updates as isolated domains and begin composing these two pathways together. Mastering this unified abstraction serves as the load-bearing prerequisite for architecting safe, continuously evolving AI systems.